Okay, welcome to the afternoon session. So next week will be Z.Dogic from Brandeis University. And he's giving 2 lectures, the other one's tomorrow.
Yes.
This one's going to be about friction of violent moments. Okay. And he deserves a prize because he arrived at 9 o'clock this morning. I put him right into the fire.
So thanks, Mark. So first I'm giving a talk. I don't know anything about friction really, and second, I haven't slept last night. So this is an experiment, right? And so what I'm going to talk about tomorrow is about active pneumatics that are driven by molecular motor. And of course, once you drive a system, you have to work against, there's some dissipative frictional forces that arise in this system. And what we realized over the past few years is by controlling the friction, which can be tuned by orders of magnitude, you really dramatically affect the macroscopic dynamics that you see emerge in the system. And so we've set up to, study something that we really don't know much about, and that's friction in biopolymers. So I'll tell you some things that we maybe figured out and things that we don't understand. So friction, one can argue, is one of the earliest sciences, And so this is an image from Egypt, and so here you have some kind of sculpture being pulled by slaves, and then you have this early Egyptian tribologist, and what he's doing is he's pouring water onto sand, and by doing that he's reducing frictional coefficient by quite a bit, and he's helping his slaves pull away this easier. And so by being smart you can and so they must have realized this because supposedly that's what they did. And so friction just goes all the way back. So Leonardo da Vinci's notebooks are full of things that we teach in introductory physics now. Is you have this inclined plane, as is shown over here, and so Leonardo da Vinci figured out some things about friction, and then a lot of people continued on, and so these are interchangeably, as far as I can tell, is called Da Vinci's or Amonton's or Coulomb's laws of friction, and I don't know. They seem to be the same thing. So what are the laws of friction that you usually learn in your freshman physics? First, friction is independent of the apparent area of contact, right? So if I have a brick and if I place it on a large surface area, or if I place it on a small surface area, and if I pull it, the frictional force is going to be the same. Then the second thing that you all know about is you can define this ratio of friction, where this is the normal force over the pulling force, and you can have a static friction and you can have kinetic friction. And third law of friction is that kinetic friction is independent of velocity. As far as I can tell, is all of these laws are phenomenologically correct, but they're all at a fundamental level wrong to a certain extent. They just work in certain limits. And so in the past 20 years, what emerged is much more sophisticated experiments. Instead of doing inclined plane experiments, you can do these experiments. Essentially, what are friction experiments at a single molecule level? Okay, and so here, for example, you have what friction is breaking up the bonds, right? In certain sense, and once you break a bond, this energy is gone. You can't get it back. And so you have a dynamical force spectroscopy, for example, where you might have a surface covered with some receptors, and you have a ligand that binds this receptor, and then you can pull with an AFM tip, and see what is the force required to break this bond. And so this would be studying friction at its simplest level, and that's just pulling a single bond, right? Another experiment that's very popular is friction force microscopy. And so what you do here is you take an AFM tip and you drag an AFM tip across a periodic surface, and you measure the forces, right? And so this tip is being dragged across presumably what's a sinusoidal interface, and so you get some information about structure of your surfaces. And again, what's even more important is, and what's going to be important tomorrow is, you have molecular motors. So these motors, molecular motors, are the smallest nanomachines that hydrolyze ATP and walk along the microtubule. And of course, what they're doing is you're breaking and reforming bonds, and they have to walk against friction. And so all these studies kind of study friction at its simplest level. It's that you're really breaking and reforming a single bond. And that's something that's very different than you take a piece of brick and you drag a piece of brick along the surface, right? And so what we are interested in, and I think maybe polymers can help elucidate some of these questions, is how do you go from breaking of one bond, which has been studied to fairly extensively, to breaking of many bonds, right? And so polymers, I think, are an ideal system to ask this question, and I'll explain to you why in a little bit. So what are the model systems that we use? It's we work with biofilaments, and so this is one biofilament model that we use and that I'll talk about today. It's an actin filament. You can see it over here. We fluorescently label all of the molecule, and it's just confined between two surfaces, and you can see how it fluctuates due to Brownian motion, okay? And so as a physicist, you see something like this, and you say, well, I'll just approximate this as some kind of coarse-grained cylindrical rod that has a certain persistence length. Persistence length tells you how floppy thing is, how long do I have to move along this contour length for the orientational correlations to decay. And so this has an 8 micromolar, sorry, that's jet lag speaking, 8 micrometers persistence length. So we physicists are very happy with describing actin filaments as something like this. And being at Brandeis, I talk often to biologists, and they just look at this and they just really, really dislike it, because their life is all about molecular details. And so maybe they'll come down and say, well, okay, I can think about an actin filament as something like this. So these are monomers. They're about 3-4 nanometers in diameter, and you can build this helix, okay? And so this, of course, has more structure than this, okay? And in EM, in a high-quality EM, you can start to see this monomeric structure of an actin filament, right? And so, but if you talk to biologists, what they really like to talk about is something like this. That's, of course, much more complicated than something like this, right? So these are the monomers, and you have this helical structure. This is a 5.5 nanometer repeat, and so this is a full atomistic model of F-actin filament. And the question is really, when is this approximation okay? When can I treat something that really looks like this as a coarse-grained filament that has no structure with it? Because as I start pushing these things together, at some point, I'm going to start to feel this, molecular structure of the filament, and that's something that we want to investigate. And so, when you make this approximation, you actually throw out an important symmetry in the system, I guess. So this has no periodicity along its contour length, right? It has, it's just a uniform cylinder. While this, of course, has a periodicity built in, and most polymers are composed of monomers, and they have an inherent periodicity. And so we are interested in limits in which this periodicity starts to emerge and what are its effects. Okay? Are there any questions so far from students? Everything is clear? The other filament that I'll talk about is microtubules. So this is a microtubule. F-actin you isolate by going to a market and getting a freshly killed rabbit or a chicken will do, and grinding it in a blender, okay? And then you repolymerize and depolymerize and spin, and at the end you have hundreds of milligrams of actin. microtubules, it's somewhat more fun procedure, is because you have to go to a slaughterhouse and you have to get freshly killed cows, and then you take its brains out and you mush it in a blender, and you again polymerize, you spin down, and you get this filaments, and then you depolymerize these filaments, and at the end of the very, very long day, you again end up with hundreds of milligrams of filaments. It's a, it's a kind of, interesting procedure. And so this is what you end up with, right? This is microtubules. They are composed of tubulin dimers, and they really make a hollow shell, okay? If I look at a microtubule from the top, the middle of it is empty, and you have these tubulin dimers that are organized into these protofilaments that point along this direction. And so this is a high resolution EM picture from a microtubule, and this is from the side view of the microtubule, and this is a EM picture from the top. Okay, and so what I should emphasize is that its biological filaments are really driven out of equilibrium because they undergo interesting dynamics. For example, the microtubules can grow and then they suddenly collapse and then they grow. This phenomena is known as dynamic instability, but we don't worry about that because we take a non-hydrolyzable analog of GTP, and so these things are static structures in everything I will talk about. Persistence length of microtubules, because they are much thicker, is millimeters, okay, instead of micromolar or micrometers. Okay, so it's these things are just thicker, and so and basically for that reason it scales with r cubed, r to the fourth. These things are just much more rigid. By themselves, these things are coated with polyelectrolytes, coated with these are proteins. They have ionizable groups, and so they are polyelectrolytes, and they're going to have high surface charge on top of it, right? And so, and that's going to stabilize these things. So naturally, they will not aggregate laterally. They are going to be purely repulsive. And so we want to induce an adhesion force, and there's many ways to induce an adhesion force, but the one that we choose is a depletion mechanism, okay? And so this is a very universal and very simple mechanism to induce adhesion between the filaments. And so, for example, here you have a microtubule, and you have polymers, non-absorbing polymers that are shown over here. That can be polyethylene glycol or dextran or anything else that doesn't stick to the microtubule. And so what's going to happen now is, if this is my microtubule, in order to place this microtubule over here, I need to displace the polymers not only from where my microtubule is, but from this shell around the microtubule, okay? And so the polymer, the center of mass of the polymer, is excluded from this shell around the microtubule. And this polymer is exerting osmotic pressure on all sides onto the microtubule. If I bring a second microtubule into my solution, the same thing happens, okay? It costs quite a lot of entropy to displace all of these polymers from this excluded volume shell. Now what happens is, if I take two of these microtubules together, they're gonna, and if I bring them in this kind of configuration, what you're gonna have is you're gonna have effective attractive depletion interactions, okay? So on the outside, I have a high osmotic pressure. Then on the inside, no polymer is allowed to penetrate into this region. And so you have an effective attractive potential. The nice thing about this attractive potential is that you can tune its range of the attraction, and you can tune its strength of the attraction. So if I increase the polymer concentration over here, what's going to happen is that the effective attractive strength is going to increase linearly in polymer concentration. And if I increase the polymer size, what's going to happen is that the range of the attractive potential is going to increase. Okay? The other way that you can think about this is in terms of entropy. Okay? So if I bring two of these filaments together, what I do is I lose entropy of these filaments because they are bundled together now. But what I do is these polymers gain more than enough free volume, which is proportional to entropy, to compensate for the loss of entropy of the filaments. And so by bundling the filaments together, I increase the free volume available to the polymer, and that results in the effective attractive interactions. Yes?
What do you mean by potential of mu force?
It's an effective potential, right? So I can average over these degrees of freedom, and if I do an experiment that I'll show you later, and if I pull these things, it's not a direct potential, it means that I need to average over these degrees of freedom. And so the other thing that's kind of obvious about the filaments, but that's really important, is that this depletion potential is for rods is highly dependent on the rod orientation. Okay, so if I have two rods, I want to bring them together. I'm going to maximize my overlap volume if they're parallel to one another, and if they are in registry with one another. If I bring them perpendicular to one another, I can't add up attractive interactions along the whole filament length, and this actually has big consequences on a lot of things that we work on. But it's a kind of obvious effect. Are there any questions about the depletion interactions?
You have some staking?
Hmm?
You have like a layer of wood all parallel, and on top of them you have resulting.
Well, I mean, it's interesting, right? If you have these monodispersed things, and if you just let them aggregate, you'll get a lot of interesting phases. That's actually something that we study in my lab, but I'm not going to talk about this. So what's going to happen is you can bring another rod here. It will want to sit here, and eventually what you'll get is you'll get a growth of rods along this direction, and you can get a two-dimensional liquid that looks like a membrane. They really don't want to sit on top of it because that kills certain entropic degrees of freedom. Of course, this is a hard rod, right? So you have this, the effective potential would be infinity when these rods overlap, and then you would have this attractive potential. But in real life, I told you that these rods are charged, and so if I bring them together, there's going to be a repulsive interaction between these two rods, okay? And so in a real life, this is how the potential would look like. Okay, so this is for F-actin filament. The F-actin filament has a 6-7 nanometer diameter. This is the lateral separation between two rods. Okay, and so you have this long-range depletion interaction that just decreases monotonically. It's a polynomial to where the separation is 0, but at very short separations, what happens is that the electrostatics, these rods are electrostatically repelling one another, and so you get this electrostatic repulsion that starts to dominate. And so if you have two filaments, they'll probably sit at a few nanometers apart from each other. They will not actually be touching each other. And so here you can see if I start increasing the polyethylene glycol, that's my polymer, if I start to increase its concentration, you'll see that it goes from, the depth of the potential increases, but so this is the same molecular weight, but if I change the salt, then this repulsion would become longer range, and then the range of the potential would, or the lateral separation between two filaments would change. Yes? This is not a measurement. This is just a theoretical prediction where you take a depletion potential from a Sakura-Ozawa and you solve Poisson-Boltzmann equation for the repulsive potential. Okay?
Sorry?
Yes?
How about the entropy term?
This is for perfectly aligned rods.
Okay.
So, but
They can do this, they don't gain a lot in entropy?
you mean within the attractive potential? I mean, what actually starts to matter is actually the undulations degrees of freedom, and you can see evidence of that, right? Because these things are semi-flexible, and as you start packing them together, what starts to matter is that you're confining their fluctuations, and you get an additional repulsion due to the fluctuations because they're confined. All right, so this is the experiment, okay? So here we have microtubules. You have one microtubule over here, you have another microtubule over here, and then you can see this short patch over here, and that's a short patch of a very short microtubule bound to this microtubule, okay? And so the polymer is all around, and you just can watch this, okay? And so you'll see, you'll see as they come together, you know, they'll diffuse around and they'll find each other, and then they will aggregate, associate laterally, and when they start to associate laterally, they contract, right? And the reason why they contract is because they maximize their overlap length, right? So if you have a configuration like this, the free volume that I save is proportional to this region over here, but if I maximize the overlap, if I contract the filament, then I maximize the overlap length, and so that's what two filaments in isolation will do, okay? And so I can write down energy of this association, and this energy of the association is equal to the adhesion energy per unit length times the overlap area, where L is the overlap area. So in this case, it's smaller than in this case. And so two filaments will maximize the overlap area. And then if you know the energy, you can ask what is the force pushing these filaments together. Okay, and so this force is just derivative of energy with respect to the overlap area, and that's going to be the adhesion energy per unit length. And so that has the right units, right? Because adhesion energy is kT per, is energy per length, so it has the units of force. And so two passive filaments, in this case, will just contract and maximize their overlap area. And so we wanted to actually measure this, okay? And the way you do that is an experiment that's shown over here. So what we do is we have microtubules, you have two beads, and you have microtubules attached to these two beads, okay? And so, and these two beads are held together in an optical trap. An optical trap is just, you know, you can think about it as a harmonic potential, okay? And so this bead is just going to sit at the minimum of this harmonic potential, and this bead is going to sit at this minimum of the harmonic potential. You can just image these beads, and you can see what is their average separation, and when the microtubules are not bound together, they're just fluctuating freely around, and you'll see that that's the red line, right? So that's the bead separation when no bundle is formed, and it fluctuates around 15.7 microns, okay? If you weigh, yes? A micron, 2 microns, 5 microns. The bead is 1 micron. So, you know, so this is 1 micron, so it's 3.5 microns or something like that. You know, I made these, you know, slides on the plane last night. So. Thank you. So I'll work on the scale bar. So you know, you wait a long time, and eventually these microtubules are going to find each other, and they're going to adhere to one another, right? And then what's going to happen is they want to maximize their overlap length, and so they pull the beads out into the trap, right? So now this bead is no longer going to sit at the minimum of this potential, but it's going to sit a little bit away from it because it's pulled by this microtubule bundle, and this bead is not going to sit at a minimum of the potential, but it's going to be pulled a little bit away from it. And so you can see this event quite clearly, right? And so here the microtubules are happily flopping around, and then at some point you see this distinct jump, and that's where the microtubule bundle forms, and then the beads fluctuate around, but at a smaller separation because they're pulled out of the trap, okay? And if I know the trap stiffness, then I can calculate what is this force. Can I go on? So it's a simple experiment, okay? Huh? It's a change of 40 nanometers. You can do, if you have an image of a bead, you can do surprisingly well by tracking it. Few nanometers is routine, right? So you can see what the noise is, and so 40 nanometers is good. Yeah. And so this is how the experiment actually works, right? So it's a little bit complicated experiment because we were getting cross-linking between the microtubules, but you know, so that took a year out of my graduate student lifetime. But you know, I don't want to bore you with this technical details. But so, you know, here you have this microtubules, you have the seeds, and here you actually have two filaments linked to microtubules, so you can also control its orientation. And so the student now has these two filaments, and now he goes fishing, which is, I guess, an appropriate, that's what I learned during lunchtime, is that, how is it called, the national, that you go fishing when you do science, or? Okay, the skeezer, right? So you go, you know, so you literally, but you know, you have a reasonable control and you can assemble this thing, okay? And so we want to measure and you can control the overlap. So, right, so if you look at this movie, so you can see now, you know, so now there are two beads over here, and the student is going to rotate one of these filaments, and now the bundle is formed. And at this point, when the bundle is formed, now we can control the overlap length, right? By just moving the beads up and down. And so this is the overlap area, and we have perfect control over this overlap area. And so, you know, so that's illustrated over here, right? You can change this is the overlap area, and here we are pulling one of the beads away, and the overlap area decreases. And so you have, you know, we can't measure it that accurately, actually. We can measure it maybe to within a 0.1 nanometer. And so the way you do this measurement is you literally take two beads, and now you just image the beads, and there is no bleaching or anything, so you can just acquire data for minutes or hours, as long as nothing else gets into your traps. And so you get a bead separation, and you see these things fluctuate around. And so you get this trace, right? And so you know from Boltzmann, right, distribution, that this probability distribution is going to be something like this, right? So where U of L naught is the bundle interaction, right? That's just the adhesion energy times the overlap length. And then you have both beads. Each bead interacts with an entropic potential that has a harmonic length scale. And so these beads, so that's just summarized in this EX1, EX2. If you do the same experiment, if you note here, again, the average is about 0.9525. If you do the same experiment in the absence of the bead, as I showed you before, the average jumps up a little bit, okay? And so here you see this average, and now you're just probing this potential energy, right? EX1, EX2. There is no overlap, so we make sure that there is no overlap in this case. And so you can replot these bead fluctuations, right? So you, as a histogram, right? So this is the probability density of two filaments being at a certain separation when the bundle is present and when you're doing a pure calibration, right? And so in a pure calibration, the average separation is again 0.975, and then when you form a bundle, what you get is you get an average separation that's slightly less, okay? And so you could just take the peaks of these values, and since you know the trap stiffness, you can calculate the adhesion energy. But you can also do much better, is you can take these probability distributions and extract you know, the average adhesion energy, which is just the log of the probability density, plus some constant. And if you do that, you get the bundle energy as a function of bead separation, which is directly proportional to the filament overlap length, right? And so you get this nice linear plot, and that's what we expected when we wrote that the adhesion energy is adhesion energy per unit length times the overlap separation, and the slope of this plot just gives you your lambda, which is 25.2 kBt per micron, okay? And this is in terms of force, right? So you can convert this into force, and it's of the order of 0.1 piconewtons, right? So it's a very, very tiny force, but it's sufficiently strong to measure. Yes?
When you measure lambda here, when you're measuring lambda here, it's only around like for a given overlap value?
Yes.
With your model, you do that with the experiment for a bunch of different overlap and check that this is...
Yes, yes. So I can extract lambda from here, and going to my, then I can vary it, I can change the, you know, overlap length by many microns, and that's so that's what my student did here, right? Is here you're measuring the bundle overlap length. Here, this is the bundle overlap length, right? And this is the depletion force, okay? And so here he's changing both the ionic salt and the depletion interaction, okay? And so here you can see that essentially, the data is noisy, and that's just a fact of life when you do experiments, especially this type of experiments. But you can see that there's essentially independent of the overlap length over many, many microns. Right? So the assumption that energy is adhesion energy per unit length times length is a reasonable one. And so you can see, for example, well, I'll discuss this data in more detail. And so you can systematically do these measurements over many, what you can vary is the two parameters that you vary is the depletion strength and the strength of the ionic the ionic strength, right? The ionic strength tells you how strongly do two things repel each other, right? And the adhesion strength determines what is the depth of the interaction potential, right? And so you can see as I increase the PEG concentration from 1 to 1.5, the depletion strength increases, as one would expect. And then as I decrease the ionic strength, the depletion, the average adhesion length decreases, okay? And it decreases in a certain way, right? And then at some point you can't even form bundles anymore, and that's because the range of the electrostatic repulsion is longer than the range of the attractive interactions between the two filaments. And you can even do it at lower concentration. You can do it for a different polymer, and it seems to have this kind of ubiquitous scaling where things kind of saturate as you increase the ionic strength. Yes, Jeremy.
Here, you said that one of the questions, can you see the discreteness and the
That's the second part of my talk.
Okay, but at this point, when you use the experiment, there's no way you can see it.
There is no evidence of it for this particular system, right? So this just behaves. Well, I mean, let me do let me show that, right? But so far, all the friction is governed by hydrodynamic interactions. Yeah. Well, I'll come to that, okay? And so this is the salt. This is a simple theory, right? That I've plotted in the beginning. You have the electrostatic repulsion, and you have the depletion attraction, right? And you can see that the scaling looks very similar to one another, right? It looks exactly like the experiments, but if you plot them on top of each other, you get very large disagreement, okay? And so this is the data, for example, for 1.5 millimolar PEG, and the simple Asakura-Ozawa and Poisson-Boltzmann equation would give you something that's almost 3 times larger. Yes?
For such small length scales, you wouldn't necessarily expect the Poisson-Boltzmann equation to make sense. Like finite size effects and everything.
No, I think it should still do okay, right? I mean, we take into account, we solve the non-linear part, right? So you don't do the bi-Huckel approximation, and people apply Poisson-Boltzmann for these filaments all the time, and so I think we're still okay there. So what's going on, we believe, is that if you look at the microtubule structures, is actually, if you read the literature, you'll discover that microtubules are covered with the disordered charged amino acids, okay? And so a microtubule surface is covered with about 17 amino acids of disordered amino acids that are highly charged, and so a surface of a microtubule filament is really acts like a polyelectrolyte brush. And so this polyelectrolyte brush, we believe, introduces additional repulsive interactions that weaken the adhesion strength. And that's something that we are trying to quantitatively model right now. And the literature on polyelectrolyte brushes is vast, to say the least. Okay, but so the quantity, there is no quantitative agreement, right? And this is our belief. What is the reason for this? Yes.
So you mentioned suppression of the transverse depletion.
Yes. Yes. Yeah, but not that much, right? So we've actually done it for actin filaments quantitatively, and it does help, but it's not gonna be sufficient. Especially microtubules are so stiff; it's 6 millimeters persistence.
You can really see that you suppress a lot.
Yeah. Yeah, I mean, and these things scale as, you know, q to the 1/4. So I mean, it could matter, right? But we haven't done it quantitatively, but I would doubt that it would decrease it by this much. Okay, so what I want to talk about now is, you know, the other experiment that you can do is you can have this bead, and you can just, you know, you have a single bead, you have a microtubule, and you pull with the flow, right? So you pull with the flow, and then you stop the flow, and the microtubule is going to retract, right? And so it's going to retract, and as it's retracting, it's working against the friction. And so I think what you can do is to describe this process is you can just say that the force, the contractile force, which is lambda, which we've measured before, should just have this type of scaling, right? So you'll get, you know, it should depend on some kind of effective viscosity of this interface times the overlap of the interface times the velocity of at which it's retracting. And so you can solve this equation very easily, and you get, you know, the prediction that says this is how the overlap length should scale with the function of time. And so we do this experiment, and this is what you observe, right? So you have an overlap length, and you have a time, and you can see how overlap length decreases as a function of time. Wait, does this make sense? So I think the experiment probably starts over here. So overlap length.
What's the experiment?
So what we do is we have a bead, and we have a microtubule, and we have another microtubule that's not attached to anything. We apply a flow, and two microtubules are pushed apart. Okay? And then we stop the flow, and then there's a contractile force that pushes the microtubules together.
But everything else is relaxing also. If you didn't have that other guy, if you did put it in the flow, there'd also be some relaxation, but it's too fast. It's much faster.
You mean the relaxation of a bead in a trap?
A bead and the microtubule.
Yeah, that's much faster, right? That would have the corner frequency of this bead is milliseconds, right? And so, but this, huh? Yeah, but the microtubule makes a little bit of a difference. But so what we are really measuring here is we are measuring the contraction, you know, the rate at which two filaments contract and work against the friction. Okay. Well, I mean, if you have just in general a hydrodynamic friction between two filaments, would scale would be proportional to, you know, overlap area times the velocity.
You want to call hydrodynamic friction something that is friction times velocity?
Yes, yes. And so you can extract an effective viscosity of this interface, and it's about 2 times the water. Okay, and so that you know, so what this shows is that this force is proportional to the velocity, and the force is proportional to the overlap area.
When you mention the filaments, can you tell whether they wind or?
I'm pretty sure that these filaments don't wind; they're very stiff, right? So it would cost.
No, because they're holistic.
Yeah, we can't tell that yet.
Like it goes through.
Yeah. I mean, no. I guess, you know, what you could do is you could label a bead and see whether the bead rotates. We haven't done such an experiment yet.
This could increase a lot the effective length.
Yes, I agree. Are there any questions from students?
No, that
Well, we all are students. But so the interesting thing happens is as you start increasing PEG concentration, okay? And so this is at the smallest PEG concentration. And so what you can do is you can also image this microtubule sliding on a long microtubule. Oops, I didn't want to. Okay, I guess this movie is not playing, but you can simply track this long microtubule sliding on this shorter microtubule sliding on the longer microtubule, and you can measure its mean square displacement as a function of time, okay? And you can see that it's more or less linear and perhaps subdiffuse at very short time scales. But you see, as you start increasing polyethylene glycol concentration, what you'll see is that this mean square displacement, so this is at 3.0 PEG concentration. This previous experiment was at 0.5 PEG concentration. You'll see that this so what does if the mean square displacement increases linearly with time, that tells you that the behavior is diffusive, right? And you can so it's just exhibiting Brownian motion, and you can relate that to some kind of effective viscosity, as Christina has showed you, as is on the board maybe still. If you increase the concentration even higher, you'll see that this mean square displacement starts actually deviating quite significantly from diffusive behavior, right? So this would be this is just a slope of 1, and this is what you measure, right? So these things are really kind of stuck, and they have a hard time diffusing past each other, as is shown over here. And then if you increase the concentration even higher, they just get completely stuck onto one another, and they don't diffuse at all past one another. And so in that sense, this more looks like a solid friction, right? Is that you really need the force to push these filaments past one another. Okay? Yeah, so those relaxation experiments were done at very, very low PEG concentration, just above the threshold, right? And then as you start increasing PEG concentration, you start increasing the adhesion interaction between the filaments, and you start seeing the systematic, that the diffusion of a pair of bond filaments becomes subdiffusive and eventually completely ceases to exhibit any diffusion. How am I doing on time? I have no idea.
15 minutes, so you still have 40 minutes.
Okay, that's good. Well, people are asking questions. And so this is the phase behavior, right? Is you have the ionic strength, you have the PEG concentration. At low ionic strength or low PEG concentration, you get no bundling. At high ionic strength or high PEG concentration, you get this regime where there's completely no sliding at all on experimental time scales. And what we really want to do is we want to study how does the mean square displacement increase as you increase the PEG concentration from this sliding to non-sliding regime. Okay, and so that's something that's for future experiments. Now I want to show you results for the other set of filaments, actin filaments, and I'll show you that this behavior is completely opposite of microtubules. And so these are the experiments that I've actually done first. And so this is a bundle of actin filaments. You see that they are more floppy. You have this bright filament. And this, so this is the overlap region. And we took this data, and the student said, well, they don't slide. And then I told the student, well, just look longer, right? And so then he looked longer, and then he said, well, they just don't slide at all. And after you watch these things for an hour, then you say, well, you really to study this interface, what we need to do is we need to pull on it, okay? And so this is the experiment that we've developed. Is very similar to the previous experiment, except that this is for an actin filament. And so here you have a bead, you have a filament, you have another bead, you have another filament. And the bead is attached exactly onto the end of the filament. And we pull this bead at a certain velocity, and we measure the force exerted onto the filament bead, okay? And you have these adhesive interactions that are holding the filaments together. And so this is how the experiment happens in real time. Okay, and so here you again go fishing, and so you have two beads, you have two filaments, And so the student is now creating a bundle. The bundle is formed, and now he pulls this bead at a certain velocity v, and he measures the force on this bead. Okay. You know, it again took us. You know, there's a lot of details involved in this, and this experiment took multiple years to solve all the linking biochemistry. And so this is what you measure. Okay, and so this is when we really became perplexed, right? So this is the experiment. This is the force that you measure as a function of time. Okay, and so time is equivalent to the overlap area. And so first you create your bundle, and you pull the two beads apart, and so there's some slack, right? And the force increases, and then surprisingly, the force stays flat, okay? And it stays flat for a very long time. So, right, I'm pulling at 50 nanometers per second, and this is over 100 seconds. So the overlap area is changing by 5 microns. And then at some point, the overlap area starts the force starts decreasing and goes back to 0, and then the filament falls apart. We repeat exactly, so what's unusual about this? First, it's a large plateau value, right? It's several piconewtons. It's 5 to 10 piconewtons at the weakest adhesive interactions. I showed you at microtubules that the adhesive interactions for equilibrium bundles was 2 orders of magnitude weaker, okay? And the second thing that puzzled us for a long time is that the force is independent of the overlap length, right? And so that's, you know, not clear why that would be. And so you can repeat this exactly same experiment, but just pull faster. And so you see the same thing, right? Is you first pull the slack out, so now we are pulling 4 times faster. You have this plateau, and then the thing falls down to 0, and then your filament falls apart. So what you've done is you've just compressed the experiment so that it happens faster. And so the other thing that you should observe from here is that this plateau force does not scale linearly with the velocity. For microtubules, if I pulled harder, right, the force would just be linearly dependent on the velocity. Here the force, you know, I pull 4 times faster, and the plateau force increases just by a little bit. Okay, and the other thing that you can do is, you know, is these things do not exhibit any contractility, right? If I pull them apart, I can sit there, and they are never going to slide back together how microtubules slid past one another. And so this excludes any kind of hydrodynamic interactions from these interactions with the overlap area, because the force does not scale with the velocity, the force does not scale with the overlap area, and so the question is, you know, what's going on? What is the basic physics here? And so you can repeat this experiment, this pulling experiment, at different velocities, right? And so the force as a function of velocity, notice that this is a logarithmic versus linear scale, and this force versus velocity exhibits linear dependence, okay? On this scale, which means that it's really logarithmically dependent on velocity, okay? And this is a characteristic signature of something that involves breaking of the bonds. And that's what people see in solid friction. And then you can increase the polyethylene glycol concentration, increase the adhesion force, and you can see the same kind of linear scaling as is shown over here. And so you can have a very, very simple model. I think this goes by the name of Tomlinson model, where you have this periodic background potential, and you have a bead, and this bead is connected to a spring, and you're just pulling this bead on the spring, right? And if you work through them, you know, and this prediction of the Tomlinson model is that the force is going to be logarithmically dependent on the velocity, right? And the interesting thing is, it's hard to extract this part because it's logarithmic, but the prefactor should give you the spacing, right? The prefactor should give you 1 over d, and d is the characteristic spacing of my free energy landscape, okay? And so I can extract that from my experiments that I do at different concentrations, 2.5, 3, 3.5, and you notice that you systematically get the same spacing d, which is of the order of 2.7 microns, okay? Yes?
In this model, what damps the part? Is some damping as well?
Yes, yes.
Do that in accelerant.
Yeah, no, this is in.
So it's in a viscous.
Yes, yes, yes. And there's this corner frequency that. And so, and there's this barrier U, but what we can really robustly extract is this characteristic spacing D. And interestingly enough, if you look at the microscopic structure of the filament, this is the spacing 2D, right? 2D should be 5.5 nanometers, and that's exactly what you get from high resolution structure of actin filaments. Okay, and so this really tells you that whatever is happening is that you're pulling these beads along the periodicity, and this periodicity is of the order of the monomer spacing in the filament, right? So you're really probing the monomer spacing here. No, what's happening here is that the monomers are if I have these two filaments, what's going to happen is that the two monomers intercalate with one another, right? And so for me, they're stuck in this local state, and for the sliding to occur, they have to locally separate and jump over this barrier, right?
Can you estimate at all how high this barrier is?
It gets tricky because it's a logarithmic term, so. Well, we don't have a microscopic theory of what is the cause of this of this potential energy. The strongest it can be is the adhesion energy, right? But one thing is that they could literally be separating, or you could be plowing through them. We don't exactly know what's happening. Yeah. Yes. Yes. Yeah. That gives me the spacing D, right? That's going to give me D, right? And am I just too jet lagged, or are you jet lagged? Or did you have too much beer last night? Or maybe
I won't answer to that question. But so you expand a lot. You have a lot of the velocity plus energy rotation.
Yeah. Yeah, but then there's this VC here, right? So it depends how you have some degrees of freedom there. So what I can get is VC times this, right? So. Does the adhesion age?
Yeah, if you put the two in contact and you pull, or if you...
We haven't done that experiment yet, but that's a possibility, right? And I mean, what I'm ignoring here is that this is helical, right? And so I'm ignoring a lot of things, right? But this seems to, at least indicate, that monomers are, I believe, the monomers, there's something where monomer and monomer interact. I don't know microscopically what it is. Yes. Take a drink of water. Yes.
Potential and also
Yeah.
if you have what you showed with the knuckles,
Yes.
doesn't it depend on how many knuckles you have?
Yes. So I'm going to talk about that now.
Do you have to get super strong ionic strength to do this experiment?
No. Actually, this is the weakest ionic strength and the weakest adhesion interaction. We observe this behavior. We can never get a freely sliding hydrodynamic interaction between actin filaments.
So you expect like electrostatic interaction to just like smoothen out the potential?
Yeah, but if you look at the structure of actin, it's pretty highly helical, unlike a microtubule, which is coated with this brush which screens its microscopic interaction. Hmm?
Like if you do not see the monomer, you see the elasticity. Your argument, you're saying that it's strongly helical.
Yeah.
But then you see like the opposite to the velocity of your elasticity.
Yeah, I mean, I don't know what the influence of helicity is, right? Because, as far as we can tell, these things are not wrapping around one another. So it could be that they intercalate locally over 4 or 5 pairs, and then there's a little bubble, and then they intercalate again. But as Paul said, the interesting part is that you're not actually pulling one bead, you're pulling many, many beads, right? And they're all interacting at the same time. And so we plotted, we can replot our experiment where we have, here is the force versus maximal force, and this is the overlap length, okay? And so this is the experiment starts here where the overlap length is very large, right? And then the overlap length starts decreasing, right? So as I increase the time, the overlap length decreases, and I renormalize the force by the plateau force, right? And so you can see that if I do that, if I plot overlap length and if I just normalize the force versus plateau force, I will get, that these things totally rescale on each other irrespective of the pulling velocity, right? And so this is the rescaling, and so you can define some kind of length scale that's independent of the pulling velocity, right? On the other hand, I can redo this experiment at different polyethylene glycol concentrations, and this length scale is highly dependent on the polyethylene glycol concentration, right? So at 3.5 mg per mil, it's very short, and at weak adhesion strength, it's very, very strong. It's very long, okay? And so we can define something, some characteristic length scale that's independent of the pulling velocity, and that it depends on the adhesion strength. And so what do we think is happening here? Is you can imagine this thing, you have your background monomer, and you have your beads, my actin beads, and imagine that they are all connected with perfectly rigid rods, right? Perfectly rigid bonds, right? And so if I pull on this, and this is perfectly rigid, all of the monomers have to simultaneously rise within this background potential, right? If I pull on it, because this is perfectly rigid, the tension is going to propagate along the entire filament. Okay? On the other hand, imagine a different scenario where I have these monomers, and these monomers are connected by very, very floppy links. Okay? And so I pull on this, and the tension is going to very quickly decay as I move along the filament. Okay? And so there should be a length scale that tells me how, in the presence of an applied force, how quickly does the applied tension decay along the filament length. And so we've done so this was with Maha's help, is we've done a simple model that I think it has a number of assumptions, but it's an interesting model in that it captures it captures an essential. So some of the behavior that we observe, and it predicts this length scale, this frictional length scale, right? So imagine that this is one of my filaments, and what I assume is that this filament just has extensional strain. And then you have this interfilament interaction that has an effective shear modulus, right? And so if I just look at a small point along these filaments, what you can think of is you can think of, what I define is I define the relative displacement u of x. Okay, and so this is the displacement over here. And so the force on this plate is going to be just how far are the bonds in my filament strained at this plate times the Young's modulus times its area, right? But the strain decays along the filament, and the strain is going to be different at this edge of this infinitesimal cube. And it's going to be, again, EA1 du dx, right? And what we assume is that the difference in this forces is going to be balanced by the shear distortion in this interfilament region, which is just this effective shear modulus of the interfilament region times A2 times the strain rate. Okay? And so you can A2 is just delta x, where delta x is my filament separation, and r is the radius of the filament, and A1 is the radius of the filament. And so I can balance these forces out, and that's shown over here. And if I just bring delta x over here, you get a very simple equation that's shown over here, okay? And so this equation tells me about the length scale, and this is the length scale that describes how fast does an applied shear rate propagate along the filament, and it depends on the effective shear modulus of the interfilament region, the Young's modulus of the actin filament, its radius, and T is the separation between the two filaments. Okay, and so this is the length scale, right? E is the Young's modulus, R is the radius, T is the filament separation, and this G is the effective shear modulus. So we know what R is, it's 10 nanometers. We know what T is, it's about a 1 nanometer. People have measured, Young's modulus of many proteins, and it's always about 10 to the 9 pascals, and they've measured it specifically for F-actin. And then the only other question is, can we estimate the effective shear modulus of this adhesive interfilament interaction? And so the way we do that is we just take a filament and we let it collapse on itself. Okay? And so if you have a large filament, it's going to collapse on itself, and it has this racket head. Okay? And so what the size of this racket head tells you what is the effective adhesion interaction, right? If I increase the polyethylene glycol concentration, you have the same kind of structure, but you can see that this racket head is much smaller. And so what's happening here is that the adhesion energy between the two filaments balances the bending of this racket head, right? And so you can very easily write down, you can write down an approximation like this, and you have the bending modulus, you have the circumference of the loop, and you have the adhesive potential, and you just, the energy of the circle, this is the bending energy, this is the energy required to bend the filament into a circle. It just scales as kappa and inversely proportional to the circumference of the loop. And that's going to be balanced by the adhesion energy. And from here, you get a very simple formula that tells you how the adhesion energy relates to the bending modulus and the size of the loop, right? And once you have the adhesion energy, what you can do is you can estimate the shear modulus by just, its energy per unit volume. And so it's an estimate, but it's the best we can do. And so if you measure that, it should be about 10 to the 3 pascals, right? And if you plug all of these things into the formula, and there's really no adjustable parameters, you get that this frictional decay length scale is about 1 micron, right? And so large G, high PEG concentration results in smaller lambda static. Any questions?
But you tested the factor of 4 pi in that case?
No, actually, you can do it more accurately, and it's just going to change the factor of 4 pi. It doesn't change any scaling. It's like 13.7. This is just for illustrative examples. People have worked on this.
Could you just estimate the hydrodynamic dissipation
Yes.
referring to?
Yes.
Is it significantly smaller than the viscoelastic dissipation?
Say that again?
Here, the dissipation
Yes, yes.
takes place along the chain.
Yes.
But you have also dissipation that occurs when the two filaments are sliding one on top of the
Yes.
other.
Yes.
Could you estimate the dissipation coefficients and tell whether the dissipation occurs in the solvent or along the chain?
Let me.
This
Well, let's discuss this after. Is that okay? All right. So what you can do in the end is, is you can actually, this is a simple model that actually I don't think you can do too much. It's hard to do analytically, but you can compute using computer simulations, right? Is you have a force F, you have your beads, and you pull with the force F, right? And so this is essentially a Frankel-Kontarova model, right? But what people always do in Frankel-Kontarova model is that your background potential goes to infinity, right? But here we terminate the potential over here, and we pull with the force F, right? And so this is our experiment, and we do the experiment on the computer simulations, we observe exactly similar behavior, right? Is you have a force, you have a time, and you see that you reach a plateau force, and then it's flat, and then decays exponentially. So qualitatively, these pictures look the same. And again, if you look at a force as a function of velocity, it again exhibits this logarithmic dependence. And so this is the last few minutes. I'm going to wrap up in 5 minutes or so. The question is, and this is maybe a bit speculative, is what we do experimentally is we are doing a dynamical experiment, right? Is we are really pulling on this filament and things are changing. The fact that things are independent of the pulling rate maybe tells us that things are, that the dynamics doesn't matter, or it's faster than the pulling rate. But what we do, when we estimated the experiment, theoretically we really estimated it was a static calculation, right? And so what I think, and these things do match in the computer simulation, and I think this is the reason, right? So this is what's actually happening in a simulation, is you have this bead, and you can see this is the background potential, and this, how high the bead is tells you what is the relative strain at that point, right? And so you'll see is the strain exponentially decays, and at some point, a bead pops over, and then you get this thing that looks like a soliton that very quickly propagates along the entire filament. So most...
looks like a soliton.
I don't know what a soliton is, right? I'm not a theoretician. I don't need to know that.
No, you do. But
oh, really? Okay.
You work the one-dimensional
Huh?
the controller model is the same way you look at it, solid.
Okay. Okay, so it looks like a soliton. It is a soliton. If Vincenzo says it's a soliton,
If you say
yeah, okay. I mean, and so most of the time, so if you look, this is as a function of time, this is the strain along the filament length, right? And so you'll see here is, the strain is quasi-static, then you get a formation of the soliton that very quickly propagates along the filament, and then you have the strain is quasi-static, and then you get another soliton. And so most of the time, system is actually in a quasi-static state. And then occasionally, the only thing that you need to do is you need to pop the first bead over the barrier, right? And then everything else is done for free, okay? And so I think that's why the energy, the sliding energy, is independent of the overlap length. But that's...
Usually, solution of that type of model
Yes.
have the kinks.
Yes.
Width depends on the velocity at which this soliton moves. That would be one way that we could actually check.
Check what?
Well, check whether your interpretation or whatever
Okay.
elastic model you're using
Yeah,
is
yeah.
consistent with these images.
Okay.
Like
Okay.
operationally, you can
Yeah.
just try to drive them fast by applying it to fiber.
You mean experimentally?
Yeah.
I could.
And see whether, depending on the velocity of the pulse,
If you
the
break
width,
two, it should go faster.
and
Okay.
the width,
Okay.
it can be calculated depending
Okay.
on the speed at which it's in.
Okay. Okay. Maybe we can discuss this. So okay. There's one more thing that was surprising, right? So actin filaments themselves are polar filaments, okay? And so they have a preferred tail and they have a preferred head and a tail, okay? And so the question is, I've just pulled in one configuration. And so this was my experiment so far. This was a barbed end, and so I've only pulled in one direction. And so we've modified our experiment in which we can actually change the relative orientation of the two filaments. And that again involves technical details, but what you find out is that the friction is highly dependent on the direction that you pull at, right? So this is the force, this is the time. You can see that the force increases, and this is for parallel filaments that I've talked so far. And then if you do anti-parallel filaments, what you see is that the force increases by almost 50%, okay? So there's this friction is directional. And again, they display very nice logarithmic dependence on the force velocity. And so this is kind of like, this is how people represent actin filaments usually, but maybe this is something that's more accurate, right? Is you should really think of these actin filaments as ratchets, and if I pull in this kind of configuration, they lock in, and of course the friction is going to depend on how do I pull these filaments apart, right? And so I think we've pulled in this and this configuration. This one is experimentally challenging. But you can see if I pull filaments in this configuration, they can't interlock with one another. And so the frictional force is very different than if I pull filaments in this kind of configuration. I have one more slide. And so I've showed you in the beginning of the talk is that friction in microtubules bundles was very, very weak, right? And I've also showed you from adhesion energy that you have this polyelectrolyte brushes that enhance the electrostatic repulsion, right? And so they contribute to something that's dominated by the hydrodynamic friction. And so what we really wanted to do is we wanted to recover the hydrodynamic friction in actin filaments. And we did that is we actually just took an actin filament and we coated it with a synthetic polyelectrolyte brush, as is shown over here. And so these are two actin filaments, but now they are modified so that they are really coated with polyelectrolyte brushes, and you can see that the two filaments now freely slide past one another, right? And so the idea is once you coat the filaments with this polyelectrolyte brush, it really screens the interaction between the filaments. They can't interlock with one another, and so then you recover something that really looks like a hydrodynamic friction. So if you follow the position as a function of time, they freely diffuse, and then the mean square displacement displays this hydrodynamic, this linear form that indicates hydrodynamic friction. And so you can estimate these things. And so why is this important? It's important because, as I'll show tomorrow, is we use these bundles to make as building blocks of our materials, right? And so hydrodynamic friction, to a large extent, will determine what is the composite property of these bundles, right? And so, for example, if I have a bundle in which in which the filaments freely slide past one another, it's very easy for me to bend that bundle, right? And that bundle, the bending rigidity should just scale as a number of filaments, okay? On the other hand, if I have a bundle where I have this permanent crosslinks, this bundle is much, much more difficult to bend, and so this bending rigidity scales as a number of filaments squared, right? And so by engineering this interactions, we see that we can engineer the behavior of our active mixtures, and we can actually tune them to go from extensile to contractile. And this is actually something that Andreas has studied in the past, and it's shown that the bundles, this PEG bundles of actin increase as a number of filaments square. So that it really indicates that this friction of actin filaments is solid-like instead of fluid-like. And so we really want to design the properties of these bundles by engineering properties of the friction itself and having greater understanding of it. And this will help us control the behavior and the dynamics of active matter. And the other thing that I want to say, and that I'll talk about more tomorrow, is now we have this machinery that allows us to put motor proteins and study what happens when you put motor proteins and you get contractions and extensions that's not driven by external forces, but it's driven internally by motor proteins. And so that's something that we are set up to do right now. So with that, I rambled on for a long time. Yes. Yes. Yeah, that's what we want to do. That's what we are doing right now. That's why, this was all a huge distraction, right? Because we want to know what is the force, that the clusters will generate on a single bundle, and hopefully that can be fed into the theories of active pneumatics in some meaningful way.
So, what should I keep on? It's a solid friction?
Hmm?
I'd like to keep on something I will remember. So
Oh, okay.
after the talk, I was also correcting a bit from my side. So
Yeah, yeah, yeah.
So
Yeah.
for me, I understood that it's a solid friction. I can see it as a solid friction.
Actin, if you look at the structure of an actin filament, it's a highly helical structure.
Yeah, but your data show that it's really acting as a solid.
Yeah, I mean, I think it can quantitatively be described by a Frenkel-Kontarova model, and I mean, that's what people usually use for solid friction, right?
And you show that it's depending on the.
And the surprising thing is that it doesn't depend on the overlap length, right? I mean, that's kind of what surprised us in the beginning, right? And the reason is that you only need to pull the first monomer over the barrier. Once you pull the first monomer over the barrier, you get this soliton structure, and that propagates along the entire filament. And, so all the other monomers hop for free, right? So you're really only pulling on the first monomer. And so, that's kind of what we believe is happening, right? But then, microtubules behave in a different way, right? Because they have this polymer brush, and actually you can chop off this polymer brush, and then you recover solid friction, right? And so it's telling us something about how we can engineer interactions between these filaments to determine how easily they slide, right? And it can change from 10 piconewtons to a fraction of a piconewton. If you use divalent cations, you can never break them apart. So it's 100 piconewtons at least, right? And so I believe that, divalent, you can induce bundles with divalent cations, and those things are just non-equilibrium gels, right? People always write equilibrium free energy theories, but these things are just like Velcro, right? They just stick together, and KT is not enough to equilibrate them at all.